everybody, and welcome back to Digital Integrated Circuits. I'm Professor Adam Teman of the EnICS labs at Bar-Ilan University, and today we'll be going over the Kahoot for Lecture 6, Interconnect. Today's Kahoot we have 10 questions, and the first is, what kind of permittivity do we want for gate oxide, TOX, and interlayer dielectric, ILD? Do we want low K for TOX and low K for ILD, low K for TOX and high K for ILD, high K for TOX and low K for ILD, or high K for TOX and high K for ILD? Well, it's going to be this one, high K for TOX and low K for ILD. So let's go over the answer to that one and see why. If we go back to our, our table of the permittivities of different types of materials, we have silicon dioxide, which has a permittivity of 3.9. Permittivity would be epsilon R, or kappa. So that's why we call it K, because of the kappa over here. And if we go up to different materials, such as aerogels and free space, we get a lower permittivity, and therefore we call these low K materials. If we go to the other side and we go towards, higher things such as, for example, hafnium, which is way higher than this, we get what we call high K materials. And what we've discussed most of the time in this lecture series up till now has been high K materials. The reason being that we want to have a very high COX. COX, which we said is equal to epsilon, R epsilon 0 divided by TOX. We wanted to have the epsilon R to be as high as possible to get as high as COX as possible. And that's because, K, our transconductance, is going to be mu COX W over L, which is going to, and I is going to be, proportional to K. So that's one reason for higher transconductance. The other reason is to improve our subthreshold slope, or our control over the channel. So if we remember, we have, the gate, and then we have the channel over here, and then we have all kinds of other parasitic capacitances, which we called as a whole C dep, and this was COX, and we want to have COX over C dep be as high as possible, or we want to have N be close to 1. So we want to have as high a K as possible. But when we're talking about interlayer dielectrics, and now we're talking about parasitics, well, we have these different types of metals that are going through the design, and they have coupling capacitance between them, and we want to have the coupling capacitance be as small as possible, and therefore we want a low K. We want to have something as low as possible. And indeed, nowadays we even have chips that have free space, that have basically etched away the interlayer dielectric to have air gaps between different metal layers to reduce this this coupling. Our second question, what kind of capacitance is most dominant or problematic in modern process technologies? Is it parallel plate capacitance, fringing, coupling, or shielding? And the answer, of course, is coupling capacitance. So again, going back to our slides, we have the impact of interwire capacitances, and we have all of these different capacitances, where some of them could be capacitance to ground, and we traditionally, especially when we had really old processes that maybe had one metal layer, we would think of a wire as one of these infinite types of plates, and then we get parallel plate capacitance. And then we discussed the fact that if this was the parallel plate capacitance to ground, that we had fringing capacitance. And that was maybe because the wires were much smaller, they got thinner, and the other thing is they may have gotten higher. But really, since we've had many more metal layers, and we have this thing where our wires do get much more tall and thin, then we get coupling capacitance, which becomes really critical and bad. So we have a lot of coupling capacitance, whereas if I go up to metal 7 or something, the distance for this parallel plate capacitance to the ground is going to be really low. And so we can see here that as the spacing between the different technologies or metal layers goes and gets smaller, that's as we advance in technology, what happens basically is that the line-to-line capacitance goes way up, while the line-to-ground capacitance goes down. And really, a long time ago, the line-to-line capacitance overtook the line-to-ground capacitance. So coupling capacitance is of course the main and dominant capacitance nowadays. So for our next question, we have some of the things we showed in the slide deck. What is the total relevant capacitance for the transition of the middle inverter? So here we have two constant voltages on these two inverters, and here we have a step function going into the middle inverter, and we ask what is the effective capacitance going to the middle inverter. And what we see is we actually have to choose which one it is, and it's going to be that C total is going to be CL plus C12 plus CC1 plus CC2. Okay, and let's see why that is. We go into this type of a scheme. We have, the constants over here. It keeps a constant voltage at these two nodes, but the voltage over here changes. And that means that we had, for example, 0 volts on this capacitor and this capacitor before the change, and after the change we went up to a 1 volt difference over here and a 1 volt or a VDD here, VDD, let's say. Okay, and so in total, basically these two capacitances went through a full swing, and so we have to add them to the effective capacitance, and so our capacitance is really going to be that C total equals CL, which is obviously going through the full swing, plus C1 plus CC1 plus CC2. With that, I'll give you a different example, and again, what is the total relevant capacitance for the transition of the middle inverter? And in this case, all three of them are toggling. While this one is toggling one way, causing a toggle because it's inverter to the other direction on the other side, the other two are toggling in the opposite direction. And what we're actually going to get is CL plus 2CC1 plus 2CC2. And let's see why that is going to be. So in this case, again, we have this toggle where the middle inverter is going to toggle separately from the other two inverters, causing a different type of a voltage swing. So if at the beginning over here we had VDD over here and 0 over here and 0 over here, that means we had a voltage swing of VDD in this direction. We could call it a minus VDD over here. And again, in the same thing over here, we had this minus VDD over here. On the other hand, after our swing, we had 0 over here, VDD over here, and VDD over here, causing us to have a plus VDD over this way, and VDD over this way. So that means that our voltage swing actually went from being, you could say, charged in one direction towards VDD to being charged in the other direction towards VDD, and making effectively this be double the capacitance over here and double the capacitance over here. So we're going to get a total of, the regular CL that's going through a full voltage swing plus double the voltage swing over CC1 and double the voltage swing over CC2. Question number 5. Why do we often apply shielding to clock nets? And please mark the incorrect answer. So is it to ensure that there are no glitches on the clock? Is it to reduce the noise caused by others by clock transitions? Is it to reduce the capacitance of the clock net? Or is it because the clock is the most important net in a digital system? And the question is to mark the incorrect answer. Which of the the 4 of these is not correct? And it's going to be to reduce the capacitance of the clock net. Again, let's go back to our slides. And we saw this nice kind of a graph over here that shows our aggressor and our victims and how they're driven. So we have some sort of a pair of nets over here driven by some inverter, and there's some sort of a coupling capacitance between them. Okay, and what this is showing, this guy is, let's say he's the aggressor, so he has this voltage swing on him, and the other one is connected, say, to a constant, let's say VDD or something like that, and here is going to be ground. And what's going to happen is, because of the voltage swing over here, there's going to be a jump on the other line. So this is an aggressor, and this is a victim. And what our graph shows over here is, depending on the strength of the driver, how much this jump on the victim is going to be, and how long it's going to take to recover and pull it back to its original level. So basically what we have over here is a problem because we're going to have some sort of a noise on the victim net that is caused by the aggressor. And the probably best way to get rid of that is to stick another line in between that's going to decouple. There's going to be capacitance here and capacitance here, but the capacitive factor that's going to go through this shield is going to be very, very low, and that's what a shield is. So this is a shield over here. And the main thing, the main reason we use a shield, again, is to protect some sort of net. And since our clock nets are really, really important, what we're going to do is we're going to usually put a shield around. If this is going to be a clock net over here, we're going to put shields on both sides of the clock net to protect it from any possible aggressors that we have outside, so they won't cause any glitch. Our problem is we're going to be seeing soon in a upcoming lecture about sequential elements is that a flip-flop type of a thing is a edge-triggered element. So when the clock rises, it samples the D over here and moves it over to Q over here. And if we get a glitch, that's going to cause another clock edge, and we really don't want that. So and besides anything else, we don't want any noise to happen on the clock net. So our main reason for using shields, and that's why we do it extensively, is to protect the clock net. But on the other hand, the clock net is also a very strong type of a net, that has these sharp transitions and so forth. So it has really big drivers, and the really big drivers are going to cause victims to get a nice spike on them. So we want to also protect other nets from them. So it also is as a secondary type of a thing to protect other signals from aggression by a clock net. So those are two things, and the clock net really is the most important net in a digital system. On the other hand, as you can see here, we actually put this shield is going to be a net that's going to be close to the clock net, and therefore add capacitance. So it for sure doesn't reduce capacitance. In fact, to reduce this effect of the coupling capacitance that we get, which causes us to have speed and power issues, RC issues, what we're going to often do is put double spacing. So this is going to be a higher space between the clock net and the shield that is around it. So the answer is going to be that we do have, this is true, to ensure that there are no glitches on the clock. It is true that it's to reduce noise caused to others by clock transitions, and it is true that it is because the clock is the most important net in a digital system. It is not true that is to reduce the capacitance of the clock net. Next question is, what is a good rough estimate for the resistance of a routing wire that is 10 micron long with a width of 100 nanometers? This is going to be 1 ohm, 10 ohms, 1 kilo ohm, or 10 kilo ohms. So if you do the calculation, you're going to find out that it's going to be about 10 ohms. Now, where did I reach that estimation? And the answer is going to be, again, in our slides, we had a table over here of sheet resistances. And remember what sheet resistance is. It's a normalization of the resistance of a certain type of a conductor divided by how many squares that conductor is. So we assume that the height of the conductor is going to be constant, and the rho, the resistance coefficient, is going to be. And so we can just show what the resistance is with times W over L, and W over L is basically the number of squares. So what we would do is we would take a resistor over here, and we have some current coming in and going out, and we would break it into squares, which is the same as taking the length divided by the width, length, as I said before. And so if we have here 5 squares, we take 5 and multiply it by whatever the number here is over here in the sheet resistance, and that would bring us the resistance of our wire. And we said that usually, we can take as a rule of thumb something like R square being 100 milliohm per square, or 0.1 ohms per square. Okay, now that is not exactly correct. So here's a table from some technology, and you see that it depends on what the metal layer is, and that's because the higher metal layers will have a higher height. Okay, they may also be different materials, and of course, if we use polysilicon or diffusions or an N-well or P-well to be our resistor, they will have a higher resistance level. Okay, so in the example that we gave, we had a 10 micron wire. okay, and we had 100 nanometer width, and that would be equal to, so that's 10 times 10 to the minus 6, so that's going to be 10 to the minus 5, divided by 100 times 10 to the minus 9 is going to be 10 to the minus 7. So what we're going to have here is going to be 100, right? It's going to be 100 times 0.1 ohms per square, and that's going to give us a 10 ohm resistor. Okay, I just wanted to mention over here that if we look at this type of a table, we have a differentiation between, silicided or non-silicided diffusions in polysilicon, and we see that when they're not silicided, they have a much higher resistance. So if you do want to make a resistor out of polysilicon, for example, if you're doing some sort of analog design or so forth, you want to put a silicide block so it will not create this silicide on top. So that's just a point to mention. Another thing to mention is that there's a large distribution of the actual value of resistance that you get from trying to make a resistor. So usually when we do this type of an analog design, we don't actually try to make a resistor that's 1 kilo ohm or something like that. What we try to do is try to match two resistors to get something like a voltage divider. So we know that the two resistors will be similar to each other if they're really matched and their layout looks exactly the same. But we don't know if it's going to be exactly 1 kilo ohm or it's going to be 2 kilo ohm or half a kilo ohm or so. Okay, question number 7. What is the most accurate model to use for the RC of a wire? At least of the models that we learned. The lumped model, the distributed RC line, the Elmore delay model, or the pi model? And the answer to that one is going to be, of course, the distributed RC line. So again, let's go back to our slides and we'll see the different models that we discussed. And this is the basic type of a model that we discussed. This is the lumped model. And what does the lumped model do? It assumes basically that the resistance of the wire is negligible. And then all of the pieces of the capacitance of the wire, we can assume that they're to some sort of a constant voltage, and then we'll assume that constant voltage is at ground, and then if they're all parallel to each other, we can just take them and sum them up together and lump them into one. The resistance would be the resistance of the driver, and all of these capacitors see the resistance of the driver as, again, one lumped type of resistance. And we saw, because of that, we're going to get, that TPD is going to be equal to 0.69 our driver in this example times, the C lumped. And that is the basic, the easiest, and the most hand calculation, back of the envelope calculation way to figure out what the additional delay is going to be that is caused by the wire. So if we want a more accurate type of a model that's going to give us a better calculation, we take what we call a distributed RC wire, where each piece of this wire is going to have some sort of a type of a R and a type of a C component, and we're going to call that RDX times CDX, right? That's going to be the type of RC that we're going to have here. And when we solve that, we get to this, partial differential equation that can be solved and show us that that we're going to get an 0.38 RC type of a constant, which is almost half of the 0.69 that we had before. Yes, all this C is going to see the R driver going to be lumped, but it also is going to have the resistance that is distributed of the wire itself. And that means that we had a really bad estimation over here for the lumped model. This is the distributed RC line. This is the distributed one, okay? That's really hard to calculate and so forth because we need to solve partial differential equations and so forth. And so what Elmore came and did, he showed that there can be a pretty easy to calculate model that gives us a solution that is pretty close to this distributed RC line. And that's the Elmore equation, right? The Elmore model. And there we take each of the pieces of capacitors where we break down our line into several R and C pieces, and they can be any number that we choose. And we see that we have, the C times the R that the current goes through, plus the next C times all the R that the current goes through, plus the next C times all the R that the current goes through. And if we make these R and C infinitesimally small, we get something like R C over 2, which is similar to the 0.38 RC we get over here. So this is the Elmore model. Okay, and that's what's really commonly used for calculating the R's and C's, especially when you have branches and so forth in our types of circuits. When we go to simulation, how do we break down, a line so it will be distributed? Because if we take this and we lump everything together, or even don't take any of the capacitance of the wire, we're going to get a really bad estimation in pre-layout simulation. So only during post-layout we can have, a well defined, type of broken down wire that's going to show the different pieces of the R and C, and then we can take that into consideration in simulation. But for pre-layout, what we should do is we should always use one of these models, like the pi model or the t model, and depending on how much you want the accuracy versus the trade-off of the calculation time, it can be a pi or a 2 pi or a 3 pi or 4 pi and so forth. But what we do here is we break down the distributed wire into a piece of R with two capacitors that each have C over 2, and then when we do an Elmore delay, as you can see here, this is times nothing in the R, but this C over 2 is times the R over here, so we get an RC over 2, which is a much better estimation than we had over here when we used just this 0.69 RC. So that is the pi model, and it's important to use it during pre-layout simulation, but it is not an accurate model. Back to our answers from our Kahoot, we obviously see that the distributed RC line is the most accurate of these models. So, moving to our next question, question number 8. What is the Elmore delay constant of the following circuit? So, we have a Vin that's going through a 100 ohm resistor to femtofarad capacitor. Then we have a bunch of other 100 ohm resistors over here with 2 femtofarad, 3 femtofarad, and 4 femtofarad capacitors. And we are looking at this path from V in to V out. And the question is, what is the Elmore delay constant? And if you go and you do the calculation, which I'm going to give you a few more seconds to do, you will find out, hopefully, that 2.1 picoseconds is the answer. So just let's look at how I got to that answer. So we're over here at this Elmore delay example, and we see that we have a 1 femtofarad capacitor over here, and what Elmore says is take each of the capacitors and see what the current that is goes through to fill them. So we have this 1 femtofarad capacitor, and to fill it up we have to go through the 100 ohm resistor, so we're going to multiply that by 100. Then we go to the second capacitor, which is over here, and even though it's off the main path, we still have to, pay for the fact that it is stealing some of our charge, I guess you could say. I call it, like the neighbor who's stealing our water from our water pipe. So we have to multiply that by this 100 ohm resistor that we go through. So we have 2 femtofarad times the 100 ohm. And then we have the 3 femtofarad capacitor that we have to go through this 100 ohm capacitor and that 100 ohm capacitor. So we get 3 femtofarad times 100 plus 100 is 200, and the 4 femtofarad capacitor that now has to go through 100 plus 100 plus 100, so we get times 300. And if we multiply all those together, we get 2.1 picoseconds, and that is the Elmore delay constant of that circuit that we showed. Ninth question, what is the problem with local wire scaling if we take a standard Dennard type model? The capacitance grows by S, the resistance stays constant, the delay stays constant, or the delay grows by S. And this one's a tough one, but actually the answer is that the delay stays constant. So let's go back again to our slides and see where we discussed that. And so when we discussed about a full scaling model for local wire scaling, we said that we were going to take the width of the conductor over here, the height of the conductor, the length of the conductor, and the distance of the conductor, which we call T over here, to ground. And we're going to scale them all by the same factor, by S. So we're going to make them all smaller by S, and that works well for a local wire scaling type of an approach where the cells are getting smaller by S, so we may as well make the connections between them smaller by S. And if we put that into our model over here, the capacitance goes down by S, which would be a good thing. The resistance goes up by S, which is not a good thing. But fortunately, these two trade off, and we get this RC, which is the delay through this which stays constant. And we think that that's a really good thing, that the local interconnect delay stays constant. The big problem with that is that when we go to full Dennard scaling of transistors, we get the fact that R on stays constant. It doesn't go up by S, and the TPD actually goes down by S. And that means that the delay of the local interconnect increases relative to the transistors, or at least doesn't scale the same way. And especially if we didn't use full scaling of transistors, which we didn't do for many years, but rather we were keeping, we were getting better speeds than the interconnect, which was a non-factor in older process technologies, at some point became at the same order of magnitude, and possibly in some cases even overtakes the delay of the transistors themselves, and that's a real bad thing. And therefore we had to go to other things like not scaling the height, changing the materials, and so forth. The problem becomes much bigger when we take a global wire scaling. So with global wires, when we took two standard cells and we said, okay, the standard cells became smaller, then the distance between them may have become smaller, so we could assume that these were that the length was scaled by 1 over S. But if we took a big chip, and the chip between two technologies of the chip, the size stayed the same, and we had interconnect that was supposed to connect these two wires over these two gates over here. Well, that did not scale at all. It stayed the same length because the chip itself stayed the same size, and therefore we don't have this scaling by 1 over S, and therefore the delay actually is going to be going up. It's going to be going up by a lot, and then the global wire delay has become dominant over any transistor delay, and therefore we have to do things like going up to higher, thicker metals in order to have lower lower sheet resistance at those higher metals in order to support those global interconnects. So the capacitance did not grow by S, the resistance did not stay constant, and the delay did not grow by S. What happens is that the delay stays constant, and that was problematic because it made it made the delay of the wires scale at a slower rate than the delay of the transistors themselves. And the final question is, how do we deal with wire scaling? And this is a kind of a summary question. It asks, do we use lower resistance materials? Do we use low K interlayer dielectrics? Do we use different thicknesses for different layers, or all of the above? And of course our answer here is going to be all of the above, which will help us kind of summarize this subject. So how do we do wire scaling? So first of all, low resistance materials. So as we remember, we used to use aluminum, which was a really good material for creating, interconnects in a VLSI process. But for years and years, we worked in order to change it to copper, which has a much lower resistance, and it's much better for electromigration and so forth. The problem is that at scaled technologies nowadays, sometimes the actual resistance of the copper is not as good as we wanted, because we have to have all these barrier layers that make sure that it doesn't diffuse into the interlayer dielectrics around it, and therefore several other materials like cobalt and ruthenium have been used in recent processes to really realize the real low-level interconnects. Okay, and that is for sure the way to go. So low resistance materials is really something that has been done. Low K insulation. So again, these interlayer dielectrics over here, they were silicon dioxide. Well, we use now other materials and aerogels and even air gaps. I mean, that's the kind of extreme type of a way where you basically etch away this, and then you have air between these two conductors, and you get a really high dielectric constant, and that's a low dielectric constant between them. So a low K material is something that is really necessary for reducing the coupling capacitance. Low metals are used for local interconnects, so they're thin and dense, and we can see that over here, that we have these low metals which really are the thin. They're whatever we can get through the photolithographic process. We may use double patterning and quadruple patterning and so forth to make these guys, and we'll have very close spacing. And we assume that actually the total coupling capacitance we're going to get and the total resistance we're going to get is going to be small, because these are really short wires. They're used for local interconnect only. We do not want to go and have one of these wires running across our whole chip, because it's going to have a lot of squares, and therefore it's going to have a lot of resistance, and it's going to dominate our delay, and it's also going to probably be very affected by capacitance to other coupling capacitance to other metal layers in the same layer as it. But we can use higher metals for global routing, which are thicker, wider, and spaced farther apart. So you can see that when we go up here, and this we would usually call an X layer, this is a Y layer, and this is a Z layer. So when we go up to the Y layers, we'll use that for intermediate routing, where we route between different blocks basically that need to talk to each other, and there we have a higher height, so we get a lower sheet resistance, and we'll keep larger spacing, so the coupling capacitance is not as bad. The top metals, the Z layers, they're usually really only used for power, for VDD and ground. We will also use them for clock trunks. So the main like trunks of the clock will also put in these really big, thick, and wide wires that can have a really low resistance, and so the R factor doesn't become that big, and it have much lower coupling because we have these large spacings between them. So we have these high DRCs between them. So this stacking type of way, where we have different metal layers at different heights with different sizes and design rules, is what helps us kind of deal with wire scaling today. But it is indeed a huge problem, and it really affects us in modern processes. So with that, we finished this Kahoot, and any questions or anything you want to know, I'm available on my YouTube channel as always. Bye-bye.